All right, hello class. Um, this is the CHL week of 517 lesson, and this should be, so we're done with the AP Physics C content, and so um, I'm going to be recording 2 more content lessons, and then we'll be working just purely on final exam, final project, etc. And so anyways, this lesson is going to be on something called Fermi questions. So these are named after a physicist named Enrico Fermi, and he was well known for being able to solve these questions really well. So what is a Fermi question? If a Fermi question is, it's just a random question that seems impossible to know the answer to, or impossible to guess. But you can actually guess it, okay? So what we want to do, so basically to solve Fermi questions, no 2 people are going to have the exact same answer, but they should be in the same ballpark. And so our goal is to get the answer within a power of 10. Okay? So in other words, you use, so you know, if the actual answer is 100 and you guess 1,000, that's good. All right? Even if the actual answer is 100 and you guess 10,000, that's actually not that bad either. Or if the answer is 100 and you guessed 1, that's not that bad. So you're trying to get within a couple of powers of 10 of the actual true number, okay? Ideally within 1 power of 10, all right? And so, yeah, so that's what we're trying to do. And you want to draw on any knowledge you have. Okay, so that's important. Literally anything that is within your memory. You need to learn how to search your memory for any random factoid or any random experience that could give you a foothold on the problem. Okay? So any random background knowledge you might have, you want to draw on. And then another important thing for solving these Fermi questions is you want to try to break your guess down into sort of like sub guesses. Okay? So in other words, when we guess at the answer, we want to try and estimate a bunch of random factors that make up the final answer. Okay, so if I asked you, well, one of the questions, the first Fermi question we're going to answer is, but to explain that, I'm just going to start with my examples. Okay, so we're going to go through 6 Fermi questions in this lesson. And so the first Fermi question is, how many words can a pen write before running out? Okay? So, how many words can a pen write before running out? So I don't want to just say an answer like a million. That would be a horrible way to answer Fermi questions, okay? What I want to try and do is break it down, break the question down into as many sub-questions as possible, guess on each of those, and then combine them together to get a final answer, okay? Now, why is that going to be more accurate? It's because if you just make one guess, and I just say a million, for example, um, then what that means is that that guess is likely to be above or below the true value. If I make multiple sub-guesses, then some of those guesses are going to be too high, some of them are going to be too low, and when we combine them all together, the net result is something that is pretty close to the actual answer because you have some are too high and some are too low. Okay, so I have a couple of two ways of estimating this. Okay, so and we're going to see how close they get to the same answer. The first method that I can think of is let's estimate it based on time. Okay, so if I think about a pen, how long does a pen last for? You can think about in your experience, if you have a pen, how long do you use it for before it runs out? And in my experience, it's approximately 1 month. Okay, so pens. So I'm going to say the lifetime of a pen is roughly 1 month. Okay, and I'm probably only using the pen 5 days out of that month, or out of each week. So, we can say I'm maybe using a given pen 25 days per month. All right, 25 days per month, or okay, and the pen lasts the entire month, and then I have to switch it. So I'm going to estimate that a pen lasts 25 days. So I have 25 days per pen. Okay. Now, how many words am I writing on a given day when I'm using the pen? All right. Well, I'm thinking about when I'm using the pen. I usually so we get about 25 days out of a given pen, and well, I would say on a day when I'm using the pen, I might have to do 2 lessons, maybe 3 lessons, and each of those lessons, like how many words? Each of those lessons is maybe 2 sides to a piece of paper, and maybe there is, maybe there is 100 words per side that I fit in. So let's say that on a day where I write, and I'm doing writing, I might write 200 words for a lesson, and then I might do 3 lessons. So that might be 600 words per day. Words per day. Okay. And so then we can see that if I multiply these two together, I get 25 days per pen times 600 words in a day, and I get the number of words per pen. Okay, so this is like 10 to the 2 divided by 4, and this is 6 times 10 to the 2. All right. So 10 to the 2 times 10 to the 2 is 10 to the 4th. 6 divided by 4 is basically 1. All right, it's a little bit more than 1, but remember, we're just trying to get a ballpark estimate to within a power of 10. So I'm going to call 6 divided by 4 1, and then 100 times 100, that's about 10. That is 10,000. So I'm gonna estimate that it's about 10,000 or 10 to the fourth words per pen. All right. So that's an estimate. Another thing I could do is I could estimate based on volume. Okay. And so I'm going to use the fact that this one is a little bit more complicated to do. I'm going to use the fact that the total volume of all the ink that I have put onto the page is equal to the volume that is within the little cylinder inside the pen. Okay? So I'm going to use the fact that the volume of the words, so that the volume of the ink in the words is equal to the volume of the ink in the pen. Okay? Now the pen is stored in a cylindrical container. Okay? So that the volume of a cylinder is pi r squared h. And then the words, well, I have a certain length of line times a certain width for the line times a certain height, which is basically the thickness of the ink. Okay, so the actual thickness of this above the page. All right. So, what would you guys say is the radius of this little tube that is holding the that's holding the ink? I'm going to say that the diameter of that is about 4 millimeters. So I'm going to say that the radius is 2 millimeters. So that's going to be pi times 2 times 10 to the minus 3. So I square that. All right. And what is this length right here? I'm going to say that because the cylinder has a length that's about that long, I'm going to say that's about 10 centimeters. That's about 1/10 of a meter. Okay, so 10 to the minus 1 meters. Okay, so the volume of ink in the pen, I get 10 to the third squared, which is 10 to the minus 6, 10 to the 10 to the so 10 to the minus 6 times 10 to the minus 1 is 10 to the minus 7. And then I have 2 squared times pi. That's like 4 times 3. Okay? Which is roughly 10. 2 times 2 times pi is roughly 10. So I'm going to say 10 to the minus 6 cubic meters of ink are in the pen. Okay? Now let's think about a word. Okay, so if I make a line with the pen, what is the width of that line? I'm going to say it's about 0.5 millimeter. Okay, because I can just visually see that. So the width of that line is 0.5 millimeter. So 10 to the minus 3 divided by 2. And then what is the thickness above the page of this line that I have drawn, of this smudge that I have made? So this one is tough to estimate, okay? It's tough to estimate. So what if you have something that's really tough to estimate? I like to just go by powers of 10, okay? So is the thickness of the ink above the page, is it a millimeter? No, if it were a millimeter, I would be able to literally see the bump. Okay. Um, is it a tenth of a millimeter? I think that I would be able to, you know, um, tenth of a millimeter. I don't. I think it's probably thinner than that. I still think that I would be able to perceive with my eye maybe a tenth of a millimeter above the page, even if only slightly. So I actually think that this smudge is roughly a hundredth of a millimeter thick above the page. So that would be 10 to the minus 5 meters. Now, why don't I think it's 10 to the minus 6? Because 10 to the minus 6 is the size of a cell, okay? Like a biological cell, and I know it's going to be thicker than that. Okay? So I can take this and we can solve for the total length of the line that you can make with a pen. Okay? So if you just made one long line with your pen, how long would that line be? So I've estimated the width of the line, the thickness of the line, and so width times thickness times length, that is the volume of ink in the line. Okay? And then the total volume in the pen, I'm estimating from the size of this cylinder. And so what I get is the length, okay, is equal to, so I have 10 to the minus 6. This is 10 to the minus 8. So I divide that over and I get 10 to the 2. And then I multiply the 2 over. So I think that a pen can write a single line that is 200 meters long before running out. Okay? So now I want to ask the question, well, how many meters is a single word? So if I were writing in cursive and I looked at the length of the word, so the length of all the pen marks within the word, what, just an average word, because different ones have different lengths, what do you think it would be? I would say that each letter needs a pen mark that is about 2 centimeters long to make. Okay. So this is 200 meters per pen. Okay. And then I would say that the average word probably has something like 6 letters in it. So what that means is that the length of a word is roughly 10 centimeters or so. Like the average word, the length of the pen stroke is roughly 10 centimeters. Okay, so that's 10 to the minus 2, 10 to the minus 1, excuse me, meters per word. Now, if I take these two and I divide them by each other, I get, I have 200 meters per pen, and then I have 10 to the minus 1 meters per word. So I'm using unit analysis here, and I can see that the meters cancel out, and I get 2,000 words per pen. All right, so 2,000 words per pen, 10,000 words per pen. Those are within a factor of 10 of each other. So if I were to take a guess, I would probably guess somewhere in between those two, right? So maybe 5,000 words per pen. All right, so that's an example of a Fermi question. Here is the most famous Fermi question. All right. The most famous Fermi question is, how many piano tuners are employed in New York City? Okay? How many piano tuners are there working in New York City? That just seems like such a random question. Like, how could you even guess it? But we want to break it down. We want to break the problem down. Um, so the first sub question that I want to answer is how many pianos are in New York? Well, I would say that how many people are in New York? Is it so to guess how many people are in New York? I'm just going to go by powers of 10. So, are there more than 100,000 people in New York? Yes. Are there more than 1 million people in New York? Yes. Are there more than 10 million people in New York? That's close. Um, that's close to the right answer. I still think it's probably more than 10 million, so I'm going to say something like 20 million people. I know there's not 100 million people in New York City, so and I think it's closer to 10 million than it is to 100 million. So I'm going to guess 20 million people, 2 times 10 to the 6th, or sorry, 2 times 10 to the 7th people in New York City. Okay? Um, and then there's one piano for how many people? People in New York are living in apartments, small apartments. I'm just going to throw out a number here, and I'm going to say that there is one piano for every 20 people in New York City. That would be roughly one piano for every 5 families. And in my experience, that's pretty accurate. About 1 out of 5 families has a piano in their house. Okay? Um, keep in mind, this is an average family. In Claremont, it's probably more than that, right? Because you guys are all so educated. Um, so I'm going to say that there is one piano for every 20 people. All right? So if I multiply these two together, so I have 2 times 10 to the 7 people in New York City, and then I have one piano for every 20 people, that means that there's about 10 to the 6th pianos in New York City. All right? Now we have to ask the question, how often is a piano tuned? Well, I would say, and again, there's going to be a wide spectrum. All right? If it's a piano at a music school, it's probably getting tuned, I don't know, once a month or once you know, once every couple months. I'm not sure. Certainly not every day, but fairly frequently. If it's a piano that is in a home, I have a piano in my parents' house, and that piano was tuned once 20 years ago. It desperately needs to be tuned, but it's been tuned once. A couple months after it arrived at the house. So I'm going to say that people tune their pianos maybe every 10 years. Once every 10 years. So one time every 10 years. So if we take this, 10 to the 6 pianos, in a given year, 100,000 of them are up to be tuned. Okay? So New York City has 100,000 or 10 to the 5th pianos that need to be tuned per year. Okay? So now let's think about how many, if we have one piano tuner, how many pianos can that person tune in a year? All right? I know from experience that it takes roughly 2 hours I think, I have a very vague memory of the piano being tuned, and it wasn't just a really quick thing. He took quite a while to tune the piano. So I'm going to say 2 hours per piano. Okay. Um, so we're going to talk about a single tuner. All right. So a single piano tuner can tune, I'm going to say 3 pianos per day, because I think each one takes a couple hours, and a typical workday is 8 hours, and you have to travel between, it's the pianos are in different locations across the city. So I'm going to say 3 pianos per day. Okay. For a single piano tuner. And I'm going to say that the person is working 5 days per week and 50 weeks per year. So 3 times 5 times 50, that's about 750 pianos per year that a single tuner can tune. I'm going to just round that to 1,000. So this is roughly 1,000 pianos per year. Okay? That a single piano tuner can do. But there are 100,000 pianos, okay, that are in New York City that need to be tuned every year. So if you have a single piano tuner can do 1,000 a year, and you have 100,000 that need to be done every year, that means that there are roughly 100 piano tuners in New York City. Okay? So there's another one that's a really famous one. Let's continue. How about how many pennies can fit in Mr. P's class? How many pennies can fit in Mr. P's classroom? Well, the first thing I'm going to do is I'm going to estimate the volume of Mr. P's class, of my class. I would say that my classroom is roughly 10 meters by 10 meters. And again, it has a complicated shape. It's kind of like a pyramid shape almost at the top, and then it's a square at the bottom, and then it has a section blocked out for that server room. But I'm just going to assume that it's basically a cube that's 10 meters by 10 meters by 10 meters, okay? Why do I say it's 10 meters by 10 meters by 10 meters? Because if you were to take a stride, a single stride is roughly 1 meter. So imagine you were walking across my classroom. It would take roughly 10 good-sized steps to get all the way across the classroom, okay? So I think the volume of my class is 10 to the third, 10 by 10 by 10 cubic meters, okay? Now, what is the volume of a penny? Well, a penny is basically a really flat cylinder. So it's pi r squared h. I would say that the radius of a penny, we can say that a penny is, roughly 2 centimeters across. Okay. Roughly 2 centimeters across. Probably a little bit less than 2 centimeters, but, again, we're just ballparking it. So that means that if the diameter of the penny is 2 centimeters, then that means that the radius is 1 centimeter. So I have 10 to the minus 2, because that's a centimeter, squared. Okay? and then I multiply that by the thickness. So how thick is a penny? I would say that a penny is roughly, it's a little bit more than 1 millimeter thick. Okay, so I'm just going to call it 1 millimeter, just to have a nice round number. Okay, so that means that the volume of a penny, 10 to the minus 2 squared is 10 to the minus 4, times 10 to the minus 3 is 10 to the minus 7. Pi is about 3. So I have 3 times 10 to the minus 7 cubic meters for a penny. All right? So if I take the volume of the class and I divide by the volume of the penny, that's how many pennies would fit. So the volume of the class divided by the volume of the penny, that's going to be 10 to the third divided by 3 times 10 to the minus 7. So that's 1/3 times 10 to the 10th. Okay, which is roughly 10 to the 9th pennies. It's about 1 billion pennies. All right. 1 billion pennies would be $10 million. So $10 million worth of pennies could fit in my classroom, roughly. All right. Let's keep going with some other ones. All right. This question is kind of dark. Okay. This question is quite dark, and it is, how many humans can the Earth support? How many humans can the Earth support? All right. So the first thing I want to figure out is I want to figure out how many joules per day for a single human. All right. How many joules per day for a single human? So a single human, it's recommended that you eat 2,000 calories per day. All right. And I happen to know that 1 calorie is 4,200 joules. Okay. So this is kind of where physics knowledge comes in. It helps to know various constants and things like that. So this is 2,000 times 4,000. That's like 8 million, which is approximately 10 million. So so you need roughly 10 to the 7th joules per day. Okay. So now the next question is, how many joules per day goes to humanity? Okay. How many joules per day can humanity harvest for food? Okay. So first of all, we need to think about the planet as a whole. So if we think about the Earth as a whole, okay, it's being hit by the sun's rays. The source of all of our energy for our food is coming from the sun's rays. And I happen to know that the sun's rays, so again, this is where physics knowledge comes in handy. I happen to know that the sun's rays provide us with roughly 10 to the third watts per square meter. okay? But that's square meter not in terms of surface area, but in terms of cross-sectional area. Because if you think about it, if the Earth bulges out in front, that doesn't mean that it absorbs any more energy. It just means that this part of the Earth absorbs the energy a little bit sooner in the day. All right. So the Earth is basically a target that is a circle, pi r squared. All right. So the radius of the Earth is about 6 times 10 to the 6th meters. So I square that. So if I take the watts per square meter and I multiply it by square meters, I get the number of watts that the Earth is absorbing. So that's joules per second. Okay? So I have 10 to the 6th squared, which is 10 to the 12th, times 10 to the 3rd is 10 to the 15th. So I have 10 to the 15th watts. So remember, a watt is a joule per second. Okay? And then 6 squared is 36. Pi is 3. So 36 times 3 is roughly 100. So, all right. So this is like 10 to the second times 10 to the 15th joules per day. All right. Now I need to multiply that by the number of seconds in a day. And I happen to know that there's 86,400 seconds in a single day. All right. That's roughly 100,000. So that's 10 to the 5th seconds per day. So that means that that the Earth is absorbing roughly, so I'm going to say roughly 10 to the, so this is 10 to the 5th, and then I have 10 to the 15th. That's 10 to the 22nd joules per day. All right? That's how much the Earth as a whole is absorbing. So now we have to think about, well, how much is going to actually go to humanity? All right? So if we think about it, we have primary producers. Okay? So primary producers are the ones that are taking like photos. They're actually directly converting the sun's rays into all right, they're actively converting the sun's rays into energy. Okay, and I would say that those primary producers might be covering, I don't know, 5% or so of the Earth's surface. Probably less than that, but I would say maybe 5%. So 5 out of 100. All right. So 5% of that is harvested by plant matter that is going to photosynthesize. And then photosynthesis is not 100% efficient. So I would say, I think it's only 10% efficient or something like that. Most motors, most like car engines are something like 10% efficient. So, so that means that, you know what I mean? So that's like, photosynthesis isn't 100% efficient. So it doesn't use all of this energy. It only harvests for building of plant matter, maybe 10% of it. Okay. And not all of that is going to humans. Right? Most of that is going to feed other animals. We don't eat all of the plants on the earth. So I'm going to say maybe 1% of that is actually used by humans, and the other 99% of that plant matter is consumed by other animals. Okay? So what I get is All right. 100 times 100 is 10,000. Times 10 is 100,000. So I have like 5 over 10 to the 5th times 10 to the 22nd. That's 5 times 10 to the 17th joules per day that humans can access, okay? And again, these factors are representing how much of the total energy received by the Earth is actually going to us. Okay, and so if we take the total amount of energy that goes to us and then we divide it by the total number of joules that a single human needs, that would be the number of humans that we can sustain. So we have 5 times 10 to the 17th joules per day for the Earth, divided by 10 to the 7th joules per day per person. And what we get is 5 times 10 to the 10th people, which is 50 billion. So I would estimate the maximum number of people that the Earth can sustain is roughly 50 billion. And we're at close to 10 billion. So all this is saying is that we're pretty close to the maximum carrying capacity of the planet Earth. Okay? So that's why I said this is a dark problem. Okay. I wrote down all my questions over here. Here's a question. What is the total length of all roads in the U.S.? All right. That's another question that seems weird to answer. Okay. So the first thing I'm going to do is I'm going to treat the United States like a big rectangle. Okay. Okay. And for the moment, don't panic. I'm going to, by the way, that rectangle is roughly 3,000 meters, or miles, excuse me, wide, and maybe about 1,000 miles tall. Okay. There's lots of ways of knowing that that's the case. I know because I've literally driven from California to Washington, and I know it's a little bit more than 1,000 miles. I know airplanes travel about 500 miles per hour, and I know it takes about 6 hours to fly across the United States. So that's about 3,000 miles across the United States, things like that. Let's assume that the Earth, or that the United States is completely crisscrossed by roads. So you have all these roads, okay, crisscrossing the United States. Okay, so how often are there roads in the United States? I would say it's about every quarter mile there's a road in a city. So again, I said for the moment I'm assuming that it's completely crisscrossing, but we're going to reduce that in a second. And so I would say about every quarter mile there is a road. Okay, so that would mean that 3,000 miles, that would mean that there are roughly 12,000 roads that are going vertically north-south. Okay, and that would mean that there are roughly 4,000 roads that are running across the United States. Okay, and so if I wanted to know what is the total length of all these roads, well, I have 4,000 roads that are 3,000 miles long. So these are the east-west roads. So I have 4,000 roads times 3,000 miles. Okay, so those are the east-west roads. And then the north-south, I know there are 12,000 roads. And each of those is roughly 1,000 miles long. Okay, so I've added those up. And what I get is 24 million. So 24 times 10 to the 6th miles of road. Okay, but that's kind of an upper limit because the United States obviously has a lot of empty space. So I'm going to estimate that roughly 10% of the United States is in a grid where there's lots of roads. Okay, so I'm going to divide that by 10, and what I get is 2.4 times 10 to the 6th miles of road in the United States. That's my estimate. Okay? So you can look it up. I don't know what the answer is. Okay, so the last question is this. How long or how much time? So let's imagine that you were you could live forever. You were immortal, okay? And your hair just kept growing out, and the hair follicles were also immortal. So your hair gets longer and 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 longer, okay? And eventually the hair is going to become so long and so heavy that its own weight will pull itself out of your skull, okay? So think about that. So the question is, how long would you have to wait for a hair to pull itself out? How long would you have to wait? All right, so that's kind of an interesting question. So the first thing I want to guess is how much force does it take to pull a hair out? So remember, 1 Newton is a small tug, and I would say it takes slightly more than a small tug to pull a hair out. So I'm going to say 10 newtons to pull a hair. 10 newtons to pull out a hair. Okay? Then, so then what does that mean is the mass of the hair? Remember, this is the force, the gravitational force on that hair. But weight is equal to mg. So the weight is 10 newtons. Okay? The mass is what we're trying to figure out, and then gravity is 10. So that means that once the mass of a single hair is roughly 1 kilogram, the hair will have enough weight to pull itself out. Okay? So when a single hair achieves this mass, it will pull itself out. All right. So now let's estimate the growth rate of hair. I'm going to estimate that hair grows roughly 2 centimeters a month. Okay? So 2 times 10 to the minus 2 meters per month. And then there are 12 months in a year. Okay? All right. So that means that my hair is growing at roughly, so this is 2 times 10, so 24. So that's 2.4 times 10 to the minus 1 meters of hair per year. That's an estimate of the growth rate of hair. Okay? Now we got to figure out, well, how much weight, how much does hair weigh? All right. I don't know. Has anyone shaved their head before? I have, or I cut my own hair. So I have some idea of if I cut off a lot of hair, like how much does hair weigh? All right. So let's say that in a given month, I cut those 2 centimeters off my hair. Okay. How many hairs are on my head? Well, it's definitely more than 1,000. It's probably something like 10,000 hairs on my head. So I have 10 to the 4th hairs. Okay. And each of those hairs gets cut by about 2 centimeters. All right. So all of the hairs on top of my head, all of the hairs on top of my head are growing roughly 2 times 10 to the 2 meters per month. All right. That's all of the hairs combined. That's a lot, 200 meters per month, but there's a lot of hairs on top of your head. All right. And I happen to know that if I cut my hair in a given month and I took that pile of hair and I weighed it, it's like a barely perceptible amount of weight. Okay. I would say that a barely perceptible amount of weight is something like 10 grams. Like you can tell that there's weight there, but it's not very much. Okay. So that means that in a given month, 1 month is approximately 10 to the minus 2 kilograms of hair. All right, so I can plug that into here. I'm just going to call this 100 meters per month. So if I plug in 1 month is 10 to the minus 2 kilograms, what you get is that you grow roughly 10 to the minus 4 kilograms of hair per meter. Okay, so that's the mass of hair per meter, 10 to the minus 4th. So I got that just by plugging in for month is 10 to the minus 2 kilograms. Okay, so now if I take the number of meters per year times the number of kilograms per meter, I'm going to get, see how the meters are going to cancel out, and I'm going to get the number of kilograms of hair I grow per year. Okay, so multiplying these together, I get 2.4 times 10 to the minus 5 kilograms per year of hair. All right, so if I take 2.4 times 10 to the minus 5 kilograms per year, and I multiply it by time, that's going to be the number of kilograms of hair that I've grown. Okay, and this is for a single hair, by the way. Okay, and so the amount of time for this to reach 1 kilogram and for the hair to pull itself out, it's just going to be this equation. Rate times time equals total amount. All right, so if I divide by this, what you end up getting is roughly 50,000 years. 50,000 years. So if you could live to be 50,000 years, then the hair would grow so long that it would pull itself out. It's kind of funny. Okay. All right, so that is my lesson for today. I hope you enjoyed that. This week's homework is going to be purely about, it's going to be a little bit different because it's paragraph answers or essay answers. So all you're going to do is just type in your logic, just like I've explained to you for those questions. There is no right or wrong answer. Just practice the method of solving Fermi questions. Okay? So I hope you enjoy, because I really like Fermi